Hi everyone, in this screencast I'm going to demonstrate how to find the equation of a plane that contains these 3 points. So I'm just going to do a very rough diagram. I'm not attempting to do this in any form to scale in any way, shape or form. So let's just imagine this is where my 3 points are and they're in the plane. So the first thing I want to do is find a vector from point A to point B and a different vector from point A to point C there. Both of these vectors would be in the plane, and I might call this little one P, vector P, and this little one vector Q, just for no reason. So here we go. P, little vector P, well that would be point B subtract point A. So I would have 5 take 3, then negative 2 take 2, then 3 take negative 1, and that's going to give me a vector which is, what's that one going to be? 2, negative 4, 4. Likewise, we will find little vector Q. Q is starting at A going to C, so it'll be C take A. So it'll be 1 take 3, then it'll be 5 take 2, then it'll be 2 take negative 1, and so this one is going to be negative 2, 5 take 2 is 3, 3, negative 2, 3, 3. Very good. Now, in order to find the equation of a plane, we need at least 1 point in the plane, easy, we have 3, and we need a vector perpendicular to the plane. Well, we don't have a vector perpendicular to the plane, we have 2 vectors which are in the plane. However, a simple way to create a vector mutually at right angles to these is to do the cross product. So we will say vector n, normal to the plane, is, and it really won't matter which direction we work with, so I'm just going to say P cross Q. And remembering that the quickest way to do this is by using the determinant of a 3x3 matrix. The first row is the basis vectors I, j, k. The second row will be the values for vector P here, so 2, negative 4, 4. And the third row is the values for Q, negative 2, 3, 3. And we want the determinant of this. So the determinant of this matrix. Remember, we are going to first of all think about basis vector I, so I'm looking at just this little group here. The determinant of that 2 by 2 is negative 4 by 3, that's negative 12. Subtract 4 by 3, that's another 12, and that would multiply by I. Sorry, that's a little bit too big. I just want to rub out that little bit of a yellow, the line that I put there. Now I want to be looking at vector J. Always subtract the second one. Imagining the central column is gone, it's 2 by 3, that's 6. Subtract 2 by 4, that's negative 8, so subtracting is plus, and that's times vector J. Then we add, so it's always plus, then minus, then plus. And now for vector k, we don't worry about that third column. 2 3s are 6, minus, that's 8, times k. So my normal vector, perpendicular to the plane, is negative 24i minus 14j minus 2k. We're ready to write the equation of the plane. If we know a normal vector, yes, and if we know a point in the plane, I'm just going to select point number 1 because it seems easiest. I'll just rewrite point A down here. Point A had the value 3, 2, negative 1. So the equation then, it will be negative 24 times x minus 14 times y minus 2 times z equals, now 3 times negative 24 is negative 72, plus 2 times negative 14, that's negative 28, and that'll be plus 2, and that should equal, I think, That's negative 98, negative 98. So here's my equation, negative 24x minus 14y minus 2z equals negative 98. And that's a Cartesian form. There we go. Now just to see how we could check on that, let's pop into Geogebra. I've entered the coordinates A, B and C for the points. There they are in three-dimensional space, point A, B and C. I then drew a vector from point A to point B. There it is, starts at A, points to B. I drew a vector with this command from point A to point C, just to make it visible. So there it is, vector from point A to point C, lovely. I then did the cross product. That's the same as what we got. Now that's a very long vector, but it's really the direction that we're worried about, and it is perpendicular to those two if I slide around. So the cross product is perpendicular, there we go. And finally, I wrote my equation for the plane, there it is. Notice the coefficients for x, y and z are the same as the values in the normal. Yep. And then remember, we get the constant by going the value of the x component of the normal times the x value of A, then the y value for the normal times the y value, and the z value times the z value. And that's what we get. So if I draw that, there is my plane, and it certainly does contain points A, B and C. There we go. I think that's all we need to do. It's a wonderful thing. The equation, Cartesian equation of a two-dimensional plane, so it's got a length and it's got a width, and of course it exists in three-dimensional space. There we go. Thanks for watching.